So this week, we're going to discuss both the t-test and the t-test and the conics of the one-sided and two-sided test. So in the you can see I scribbled all over this because in the last class I discussed it extensively in regards to the theory behind it a bit and then also the applications. I will say that, and the reason I'm going to start with this, the theory about the t-distribution is because it will inform some of the checks that Ken will ask you to do. So for instance, he'll say things like, should you have used a t-test? And you should ask yourself, did your actual data demonstrate the features that are behind the theories, right? So for instance, a t-test is given to as z over, chi squared. So it's a ratio of a normal distribution in a chi, which means that we're automatically, assuming or in some sense, demanding that our population is normal. And we should check these things, right? So if we sample in such a way that, if we sample and our data doesn't look quite right, we can ask ourselves, right, whether or not our initial assumption was valid or in some sense violated. And what does it mean, right, for the scope of the t-test, right? So within the one-sided t-test, we do actually want to see that our distribution is somewhat normal, right? Although I will say that looking at the t-distribution, you can see that it has a couple of key differences from the z-distribution. So first of all, notice that the distribution you're used to working with is a z-distribution. You can see that it is the one that has short tails, right? So from -3 to 3, which is where most of the mass of the normal distribution is, the tails are getting less and less, the mass and the tails are getting smaller and smaller as you move out to the extremes, right? So in contrast, you can see the t-distribution is robust to outliers, right? You can see that it's flatter in some sense, especially in lower degrees of freedom, it can be flat. That when the distribution is, when your degrees of freedom actually is getting larger, it actually looks more and more like the normal distribution. But anyways, notice that it does actually do okay in regards to these outliers. So it's robust because it has masked the tails in the way the z-distribution does not. So we like to use it. If you do use if we're in the context of like two-sided or two sample t-tests, we need to check a couple of things. First of all, right, we need to ensure that we are actually we have two independent samples. This is why I actually have X independent of Y. The things we're sampling from should actually come from independent populations, right? So if you have a correlation structure between your actual samples, there's a different t-test for it. It's called dependent t-test. In the independent t-test setting, we have to assume that the samples that were drawn for, samples X and Y came from two different independent populations. Moreover, we're in this notion of, we also assume that not only is the distributions of both of those two things, the population at the population level somewhat normal, because again, of the ratio of the normal and the chi, we also assume that the variances are the same. And this is not a trivial assumption, right? Because if the variances are not the same, then the nature of the t-test is going to change. And so one thing that Ken had asked me to discuss today was the distinction between the pool t-test and the Welch t-test, because you should determine for yourself when you can use one and the other, when you can use the other within the scope of your data, right? So the t-test, we're going to use it primarily in the Conic hypothesis testing, and you guys know from B57 that one thing Mahinda likes to say a lot is he likes to talk about the notion of the extremes, right? So what's the probability that you observe an observation as extreme or more extreme, right, if the null hypothesis is true, right? So what does it mean to say extreme or more extreme if the null is true? Well, let's deviate, or let's detour to this notion of a null distribution, right? So we are always testing the hypothesis on the null, basically, right? So we have to, imagine in some sense, right, that the distribution we're looking at for our quantiles is the null distribution. It's not going to be the distribution on the, it's not going to be the distribution on the alternative, basically, right? So what does this mean? It means that this is the most plausible value. And and it's not an axis, it's directly in the center, right? So if you can imagine that this p-value approach is really saying, if the null hypothesis is true, and we're going to imagine that on this distribution it's true, the observations that happen in the tail are kind of somewhat unlikely, right? You shouldn't have seen those observations on the null, in theory, if the null is true, because the mass associated with those particular observations is very low, right? So now keep in mind that this is a bit of a quagmire because you're only really seeing one realization of the data, basically, right? So technically speaking, the next time you take a different realization of the data, you could get a different p-value. Of course you will, because the data is actually different. Right? This is obviously a sampling error, but we think that, even if we only saw one realization of our data, the odds of seeing an observation that's that far in the tail, if the null is true, is getting less and less likely. And this is the notion, right? So every t quantile has an associated p-value that sits across the distribution. And the most common observations are the one where what you observe directly aligns with what you hypothesize. So if you hypothesize mu naught is equal to mu naught, then of course, whenever x is exactly equal to mu naught, that is the most plausible value under the null distribution. So this is why it has the most mass. So any observations that sit close to this null are more and more likely. So when you have observations that are close to the null, you're not going to reject the null hypothesis. But your curiosity is piqued when you get to the extreme ends or the unlikely observations you see here or here, right? And this is going to happen when your t statistic is either very low if it's back here or very high if it's up here. And the associated with p-value for that will be significantly less than alpha, right? So what is alpha in this context? Alpha is the probability of making a type 1 error. That means that the null is truly actually true, but you reject the null hypothesis, right? So you don't want to make that mistake too often. And of course, when your evidence substantiates the assumption, substantiates the ability to reject the null hypothesis, you should expect that you're getting further and further into the tail. So your t values are either very, very big. If this ratio is, if this x value is very, very large, or if this x value is very, very small in this end, it's also largely negative, right? So this is how we refer to as evidence. Like you want to see things in the tail to even think about, you're not going to think about rejecting the null hypothesis. The observations are over here. You just don't have the evidence to do so, right? So let's go to the actual applications and see how this would work in the context of like the empty cars data we looked at last week, right? So I'm going to do both a one-sided and two-sided test. So first of all, somebody asked me last tutorial, what do you do to hide the tidyverse warning? Because I noticed at this time I couldn't hide the warning. So I'm going to say that I use this function here. It's called default W, get option, warn. And when you put warning equals -1, it does hide the actual the warning that loads. So you obviously don't want the tidyverse to load the packages and stuff. If you put this thing here, it actually blocks out the warnings. I'm going to post these obviously into my GitHub, but I figured that would let people know, obviously, because I'm going to post a recording, so that means people in the previous tutorial will also see the solution to the problem. I also got a question where somebody said, I don't know how to knit to PDF or knit to HTML. The features are, the default is given to you here. In the default I have here, I can either knit to HTML or PDF because I put them both as defaults. If I remove this feature, then I'm only going to knit to HTML. Similarly, if I remove the HTML, then I'm automatically knit to PDF. Now, keep in mind that if you don't have LaTeX in the background, so I have LaTeX, right? So if you see, I do have TAC, right? So I use Text Studio, but some of you may not have TAC on your computers. So one thing you can do if you want to get TAC, and I think Christina was one who had a nice idea where she said that, you can use the packages here and click on things, right? So what you might want to do if you want to find packages is, I'm going to say there's a package called, so I'm going to put it here. You can either do it here or, as Christina said I think it was 2 weeks ago, you could go to the update here and go and look for the package literally manually, but I think it's called Tiny Tac. So if you don't have that LaTeX and you want to use LaTeX on your computer, there's something called Tiny Tac that actually drops LaTeX right into your R Markdown. You can feel free to, use that. Cool. So, Liza's such a sweetheart. She's a prof in the stats department. Okay, so here's the library. I'm going to download tidyverse again, obviously, because I like to use external packages. In particular, I'm going to use both ggplot and Tibble. Okay, so this is the data from last time. I'm going to run it. And keep in mind, if you want to actually use the variables without having to actually use the $sign or without using a pipeline, right? So the $sign in the base R is equivalent to using the pipeline and tidyverse. And if you want to avoid using those two things, you might want to just attach your data first. That's why I'm going to attach empty car, so I can just call the variable to having to actually do the extra work, because then it will be within the global environment, right? So it will, when you do that, R actually takes, attaches the data set within the global environment, and you can kind of use it in there. Okay, so like I said, we should really actually be a bit careful. Oh, there's a question. Yep. It will be posted. Yep, they're going to both be posted. Absolutely. So I just wanted to point out that, like I said, we should not cheat. We should check to see if our variable is actually normal. And actually, Ken will ask these questions. He'll say things like, are your assumptions violated? And you want to check if it's true. Like, is it true that the distribution is normal? Is it true that, things look, you have equal variance if you're doing an independent two sample t-test. So we have to check these things. So I'm going to do that with the variable. So I'm going to use a couple of variables. So, I'm going to use, one thing I'm going to go the empty car. So this is the variables I'm going to use. I'm going to use weight of cars. I'm going to use engine. So VS is whether or not the engine is straight or V-shaped, right? So because I'm going to use this variable when I want to do the two sample t-test. I should also point out that, so let me talk about when I get there. But so let's check to see with the one sample t-test. Let's see whether or not our box plot for weight is actually normal, right? So this is what I achieved. Does anyone notice anything interesting about this box plot? What do you see? What do you guys notice? Is this normally distributed? Yeah, there is some skew, right? So we have to be a bit mindful of this, right? So this is actually a skew distribution. How do you know this? Well, you can tell this because, first of all, your actual black line represents the median, right? And as a student pointed out, there are outliers outside of our whiskers. Remember, these whiskers correspond to the upper and lower fence. If you use the 1.5 times IQR, right? And so Q1, minus 1.5 times IQR, Q3 plus 1.5 times IQR. So this is actually Q3 plus 1.5 times IQR is this upper fence here. And notice that there are outliers outside here. And obviously the median is closer to Q3, which is this upper part of the box here, than it is to Q1, which is down here. So we automatically are a bit intrigued, and we're thinking to ourselves, well, is this skew going to be a problem if we want to actually talk about one sample t-test within the context of normality, basically, right? So I did say that on some level, the t-distribution is robust with some outliers. And the way you can kind of imagine this is because if you look at the actual distribution, it does have fat tails, right? So maybe on some level, we can kind of accept or accommodate this outliers, but it depends. We probably have to do some more data analysis to really feel convinced. But I'm going to just pretend that I'm okay with it and see what happens. But if there was a follow-up question on your assignment, yeah, you should be thinking about whether or not you actually performed an appropriate test relative to the actual features of your data. And just to confirm that we actually have this skew, I'm going to actually run the histogram. So this is the built-in base R. This hist of weight is obviously built in. And you notice that you do have some skew, but it's kind of funny because to me, it could almost pass something that looks uniform, right? So it's hard to know, right, if it's true, if I truly think it's skewed. Maybe because the sample size is somewhat small, that I'm, it's kind of hard for me to be convinced completely that it's skewed. I could almost say it looks uniform to me, but yeah, so this looks a bit uniform at the same time, right? So I don't know if I can necessarily say it's completely skewed, but if you want to use ggplot because it makes things look nicer, here's the same, histogram, but now I'm going to put the fill as red. I wonder if I can even put color. Let's see if it works. Equals, I don't know, black. I wonder if this works. I might have to fiddle around with things, but let me see. Yeah, so let's see what I get. Okay. Yeah, so you see it does that. So I like making plots look pretty. It's like and red's my favorite color actually. So anyways, what I did was I made the fill red, but the color on the outside of the box plot looked black. So if anyone's kind of curious to make their plots look really nice, right, you can obviously play around with the features. It's the same box plot you saw as the previous one, but now it looks so much more superior, right? It looks a lot prettier and eye-catching. Yeah, so I'm going to check the mean of weight. That's because, okay, so full disclaimer, it's really not good to look at your data before you actually perform a hypothesis test. But that I mean that you should not actually glimpse to see if your data is actually looking, you should not peek at the actual features of your data before you make a test, right? So you start to have in your mind, based on empirical evidence, what you think the actual hypothesis of where you think your parameter actually sits. Because this is a test about where you think your population parameter actually sits, right? Relative to what you actually, and this is what you're doing. So is it true that your population parameter is actually this, or is it not, right? It's you're actually asking. So you shouldn't actually look at your data and use one realization of your data that for such a small sample to make a conclusion about your hypothesis, right? So I'm doing it because obviously I want to perform a test that is going to get a certain answer, but it's bad statistics, right? So don't do it. I'm just doing it because it's an illustrative purposes, but I would never actually peek at my data and then choose a hypothesis based on the data I saw. That's not right, right? Because it's just bad statistics, so to fish for an answer. But yeah, so if I run this, the mean is 3.217. Keep this in your mind because I'm going to run eventually the t-test, and it's going to show you that same 3.21 within the actual built-in base R function. Okay, so I know the mean is 3.21. This is why I'm going to perform a test about whether or not the mean is different from 2. So this is why you have mu is equal to 2 here. The test I'm actually performing is the following. So I'm performing the following test. If I just kind of pull out my pen, I'm doing the following test. The test I'm actually doing, right, is okay. OneNote sometimes gives me so much issues. I'm gonna figure it out though. Okay, here we go. Okay, so I'm doing the following test. Mu is equal to 2. That's my null hypothesis, and I want to show that actually, no, it's the alternative. Mu is not 2. So this is the test I'm performing, which means that within the scope of my null assumption, what I'm actually hypothesizing, right, is that, I think that any observation that is kind of hovering around here, right, I suppose it's inside of this region here, let's color code it. Right, so anything that's in here, I'm probably not going to reject. And what is this? Well, in the scope of my actual t-test, it's going to be a situation where, t is equal to, whenever I take an observation that's close to 2, it yields t is equal to 0. So any observation that's close to 2 is going to actually be sitting in the center here, right? Okay. So now let's see how this looks in R. And so this means that when I run it's t.task, this is the function, this is the variable I'm interested in. It's called weight. And let's remind ourselves, it is weight of cars per 100 pounds. So technically speaking, I'm really asking, is the mean different from 2,000 pounds? Not 2, right? This just, obviously I'm going to shrink the unit so it's digestible. Okay, so let's run it and see what we get. We get a couple of features. So I wonder if it's here. Yes, here we go. You get a t value, and this is a two-sided test. So really what we're actually looking at is the following. You're looking at the absolute value of t, right? So what you're truly actually looking at is the absolute value of t is equal to 7.03. And let's suppose, so, you know, within the scope of our actual distribution, so let's say that's somewhere here. Let's suppose our actual p-value is here. So let's say this is the rejection region. And our actual test statistic is somewhere even further than that. So let's say it's somewhere out here. This is, you know, t is equal to 7.03. So whatever the t, so this blue line you see here is going to be some critical value, basically, that we're going to compare our observed t value as. This is t critical. And t critical has a degree, has the following characteristic. It has degrees of freedom. Oh, you know, that's the slide. It has degrees of freedom equals n minus 1. And it has alpha level of the following, right? So this is actually this. So whenever your t value is bigger than this, it's going to be associated with, you can see from the graph, a very small p value. This is why we concern ourselves with a p value that is less than alpha, because if your p value is actually bigger than alpha, you're somewhere in the region behind the blue area, which is too close to the null assumption, basically. So you're not going, if you're too close to the null assumption, there's no reason to reject the null hypothesis, basically, right? So this is what we're looking for. So going back to our code here, you can see that the t value is 7.0374. The degrees of freedom is 31, and this is because we have 32 observations. Now to see that this is true, if I go to dimension of MT cars, you're going to see that it's 32 by 11. That's because there are 11 variables, but there's actually 32 observations, right? So obviously n minus 1, as I point out here, right, is actually correspond to 32 minus 1, which is 31. So that's one thing to note. And the p-value is given to you as this. So your p-value is, of course, less than, you know, like 0.05, which you guys know, you guys take to be the standard of reject null hypothesis. So in this context here, we're going to suppose that our true mean for weight is far from 0. Or sorry, not far from 0, far from 2. Now, this is not an accident because we know the true mean is 3.21725, as we see here. And actually also ran the computation a bit earlier above. Right? So it's not an accident that we get this. What else do you actually get? You get the features of the actual confidence interval, basically. So one thing Ken's going to show you guys is that there's a duality between the confidence interval and this notion of a t-value, right? So when your t-value is bigger than your actual t-critical value, which will correspond to a p-value that's less than alpha, then you will actually reject the null hypothesis. Similarly, when your confidence interval does not contain your hypothesized mu, as in like this confidence interval, this is the interval you constructed based on the evidence that's your data. Your data is the evidence, and here's the confidence interval you constructed. Now, if your interval does not contain your hypothesized mu, you may actually begin to think, well, does that mean that 2 is not a plausible value? Because this is an interval that tells you if you sample many samples of size 32, 95% of the time, your actual parameter for the mean is going to be inside this interval here. So what you're actually saying is that 95% of the time, it does not contain 2. This also substantiates this idea that you may think to reject null hypothesis when your evidence is telling you that it may not actually be true, basically, right? So there's a duality in there, and that when your interval does not contain your hypothesized mu, then you will tend to reject the null hypothesis. Basically, you're gonna see that a lot in your assignments coming up, right? So keep your eye on this p-value. I'm not going to talk about it just yet, but I will actually talk about it in a moment. You're going to see something funny happen when you look at the two-sided test, or when you look at the two-sample test. You're going to see interesting things happen when I change the question just a bit, right? So now this is a two-sided test. Notice that R implicitly does a two-sided test. If you do not specify the direction of the difference, it's going to assume you have a two-sided test, right? So now we actually tend to do two-sided tests, right? Because it's more conservative. If we don't have any evidence as to why we might want to do a one-sided test, we should not do it, right? So we should only do a one-sided test when we have some kind of evidence that kind of leads us to believe that, you know, we have a direction of the actual effect. Otherwise, many scientists tend to use a two-sided test just to be conservative, because a one-sided test, as you'll see shortly, is actually a less conservative test, right? Yeah, 1 second. Okay, so let's change the direction. Let's just change things slightly. Now, I'm going to say that I already knew from the mean, when I took the mean of weight up here, I knew that the direction of the effect, right? I knew that it was already bigger than 2. That's because I knew the mean was 3.125, and it was corroborated when we looked at the actual t value here. You can see that we know the mean is 3.21. So, you know, let's change the test a little bit. Now, what if instead of actually having a one-sided test, I specified a two-sided test, right? Oh, no, sorry, let me repeat that. Instead of specifying a two-sided test, let's change it to one-sided test. And so now let's see what happens if I specify the alternative is greater. So this means the default is actually, right, to give you a two-sided test. I'm going to change it to greater. And when would you actually do this for your homework, basically? If Ken says something like, you know, the difference is greater than, or the difference is less than, or check if it's more than or less than. These kind of keywords will tell you have a one-sided test, right? Otherwise, if you see words like different from, it's a two-sided test. So scan the question carefully to determine whether or not your test is one-sided or two-sided. If you see things like, is a difference, you know, bigger than, whatever, is it less than, you know, you have a one-sided test. So I'm going to pretend to have a one-sided test and have a run and look at what I see. Okay, so you can see something interesting. Does anyone see what changes in the output and what stays the same? So what do you get what do you see that's actually, what do you see that's actually the same and different? Yeah, so do you know why it has infinity? So that's a good observation to have, obviously. Does anyone know why it has the combination has infinity? Okay. So the reason why it has an infinity is because of the actual nature of the test. So this is the original test. You're asking yourself, mu is equal to 2 versus mu not equal to 2. Well, I'm going to claim the question is now the following, right? So what you actually have now is h naught mu is equal to 2. But now instead of actually different from 2, you're actually asking the following, bigger than 2, which means the lower bound is 2. But actually, upper bound it can be anything. It can be even infinity. So you're going, your intervals now, you're hypothesizing your intervals between 2 to infinity, right? So you now don't have a finite upper bound to the direction of your actual mean, basically. This is why your confidence intervals now has a lower bound of 2.92 and an upper bound of infinity. It can really take on any value, basically, right? So this is something to be cognizant about. And does anyone else notice another thing that's kind of interesting about this output? What happens to p-value? So the t-statistic is the same. It's still the 7.03, and to confirm that it is, I'll show you the plot that I did before. You can see that the t-value is always 7.03. But now the t-value, right, is not that. It's now the t-value is the same, but the actual p-value is half, basically. You might say, why is it half, right? And the reason why it's half is because of the following, right? So I now have, before I had the following, before I had the absolute value of t, it was actually taking the t value, it was before I was doing the absolute value of t, which means that it took 7.03 and all the values above it, as well as all the values below negative 7.03. But now, because it's a one-sided test, it's only really considering the values that are, you know, above. It doesn't really care about the values that are below. And so beforehand, what you were actually doing was like 2 times t bigger than t, basically. Right, so the previous thing was, it was 2 times t bigger than t. That's what you were doing beforehand, right? And so let me change it. Let me make this look a bit better. It was 2 times t bigger than t, right? And so if I actually make this a bit more, if I make the formality a bit, right? So you actually have was the following. You had t bigger than the absolute value of t, and you multiplied it by 2. Right, because it's the Gauss, t is a symmetric distribution, which means that the probability on one side is proportional to the other side. If you're looking at negative t, of course, proportionally, the area behind negative t is the same as the area above t. And so when you multiplied it by 2, you got the t value, the p value we had before. And if I look at the console, it's probably there. So you had this 6.677 times 10 to the 8. But now we're actually looking at like, well, a one-sided task. So you have to divide it by 2, which is why you actually see this, right? So this means implicitly the two-sided task is more conservative. If you don't have evidence to believe that the one-sided task is true, don't use it, because obviously you're more likely to find an effect because it's a less conservative test, right? When you multiply things by 2, it becomes more difficult to actually satisfy the less than alpha criteria, obviously, right? So I also want to show you how the actual p-value is generated, basically. Right, like I said, you're comparing your actual t value, right, to a t critical value. So what t critical value are they comparing it to? Well, they're comparing it to the following. So this t critical value you're seeing here of 7.03, well, they found out on a t distribution. The function they used was the qt function, right? So qt is a built-in function in base R. And as long as you give it an alpha level and a degrees of freedom, it will give you a quantile. So what is the quantile for, or what is the t value for the for the alpha is equal to 0.05? Well, for alpha is equal to 0.05, you're looking at the 97.5 percentile, right? Because of course you're looking for the outer 5%, which means you're looking for 2.5% above and 2.5% below for a two-sided task, right? So I'm going to specify an alpha of 0.05. Now my quantile is 1 minus alpha over 2, which makes it, I'm looking at the 97.5 percentile. So if I just run this in the console, I get the following, right? So notice that it's 0.975. I'm going to give this quantile to the qt function with the degrees of freedom, which is the size of the observations I have in my set, which is 32. This is 2.039, right? So this means that this t critical value here is actually 2.039, right? So this is actually 2.039. So this thing here. So what you're actually saying is that the p value associated with the quantile 7.03 is less than that of 2.039, but it's obvious because look at the actual positioning on the t distribution. This is a further up base, it's more to the right. So obviously it has a less mass associated with that quantile. This means that the observations to the right, which is the blue region, is getting more and more unlikely if the null is true. The observations in the red are the ones that are plausible under the null because they're very close to the null, right? So given the evidence we see, we're going to reject the null hypothesis, and we're convinced in some sense that maybe our mean is far from 0, or far from 2, sorry. Now keep in mind, again, this is only one realization of the data. We should not assume that this is fail-proof, because the only way to be fail-proof is if we only have to deal with one sample. But there are actually many samples of size 32, and obviously there's a certain amount of time where we could be wrong. It could be the case that this is the one sample where we saw an effect, when in fact the other samples tell us that we don't reject the null hypothesis. There's obviously a chance, right, that we made a mistake. We just think that it's going to be very small the more evidence we see within our fixed sample of size n. Okay, now let's change the topics a bit and go to two-sided or two independent tests, two sample independent tests. Right. So first of all, I'm going to point out that we have to do a bit more for an independent two sample t-test. Let me just say independent two sample t-test. A little bit more, by that I mean that if we go back to the slides I kind of posted here, we have to check, right, if the sample, if we want to use, for instance, a pool t-test, we need to check if the actual variance is the same or similar. And we have to actually also convince ourselves, right, that the populations of X and Y are independent, right? So we cannot be sampling from the same population, because in that way there'll be a correlation structure, and then this becomes a matched t-test, right? So if we're assuming that we have independent two-sample t-test, we have to convince ourselves that we haven't actually drawn from the same population and then told ourselves that it's independent, right? So, but in this context here, in the example I'm looking at, it really actually is independent, because the engine cannot be both V-shaped or straight at the same time. So now you can see why I picked a VS. Your engine cannot be both V-shaped and straight. So they're independent, because you have to either be one or the other, basically. So that's why I chose that. So that means the thing I checked then, other than the independence of the actual samples, is that standard errors are actually similar, right? So because this notion of this notion of similar variances is not a trivial one, right? So if your variances are not actually similar, you're looking at a Welsh t-test, not a pool t-test, and that does actually change it. It could actually change the nature of significance, right? If you're, we have to be a bit careful here, be a bit picky, right? So if we don't have similar variances, we should not feel confident necessarily to use the pool t-test, in which case we should use the Welch test. I will say the Welch t-test is the default in R. So if you don't specify variance equals true, it will assume the variance is false. And this means that the default in R is to perform a Welch t-test. So if you have to check if your variance is the same, and if you're convinced your variances are equal, then you could use you could say variance equals true and do a pool t-test. But I digress. Let's first check. Let's first fix our data to look nice. So this is the Tibble. I'm gonna pull out the variables I'm interested in. So like I said, I want to compare the weight of cars for engines that are V-shaped versus straight. So I'm going to make a Tibble with that variable, and then also with weight, and those are the only two variables I'm interested in for now. So here's my data. There are 32 observations. So like I said, if you weren't convinced that, right, there were 32 observations, now you can see that there's 32. And then I'm going to split my data into two different groups. The first group is going to be the V-shaped engine. So this is a group where the V-shape is equal to 0 is the V-shaped engine. And then when it's 1, it's straight. So I filter, so I'm using the tidyverse again. So this is data I'm filtering based on the V-shape is equal to 0. So this means that it's V-shaped. And then if it's 1, it's straight engine. So let me run this. So this means, now you can see that group 1, which is the straight engine, only has 14 observations, and group 2 has 18, right? So now this means we need to be a bit careful with the sample sizes here. The sample sizes are not equal, right? So, I'm going to check the standard errors distinctly for each group and see if they're comparable. To be fair, technically speaking, if I need to be a bit more rigorous about this, but I'm going to bypass that for now, because I don't think Ken's going to ask you to do a formal test yet to check that the actual variances are actually equal, like, because there's obviously a formal statistical test for it. You shouldn't just visually check and say, oh, they're equal. You have to check with a test, right? But I'm going to check the standard errors, and the standard errors given to us is the following. So I wrote this formula here. It's the standard deviation of your actual variable divided by, so let me put standard deviation of like weight divided by square root of n. So this is obviously standard error. You guys know this formula is what we have. That's what I've done here. So for each group is going to have a sample size n that depends on their size of obviously of the set. So group 1, they only have 14 observations, but group 2 has 18. So I cannot divide by the same length. This is why I've divided by the square root of the length of each particular group, right? Notice that the standard errors are pretty comparable, right? So, I mean, I should formally check, but I'm pretty sure that I feel reasonably okay with assuming equal variances because they look kind of comparable to me, right? But I shouldn't just blindly rush. I mean, if I want to be very specific, I should be checking basically, right? Yeah, so I just want to point out the reason, I want to point out if I remove these two features here, so if I remove alternative equals 2 dot side and variance var dot equal equals true, if I just remove these two things, this is the same thing as this. So the test, and we can actually check and see just to run, let's not skip steps. So you can see that I get this, right? So the default is to do the following, a Welch two sample test. Right, this is the default. again, so if you don't specify a variance equals true, it will literally assume that you're doing a two-sided task with unequal mean. So this Welsh, let's make a note here that, you know, the default is Welsh. The default is Welch test. So this is unequal variances. So if you don't specify, it will assume that, because that's the safest bet. The safest bet is to assume you don't have equal variances. But now let's go back and see what happens. This means that if I go back and add these features, right? So if I go back to my initial thing here and add the features back in, right? Then it will give me the same output because, like I said, it's the default. So you can see that if I put alternative equals two-sided, it's already a two-sided test it gives you. And if I put variance equals false, right, then notice that you get the exact same output because, again, it is the default. This is already the default. So the reason why I put this here is because if I change things, I can get the different output. So these two things are equivalent basically. But now let's see what happens if I put variance equals true. This is a pool test. This is actually, so two-sided. I'm going to put this here. So this is now a two-sided pool t-test, right? And what do we get? Let's run it and see. See how the p-value changes, right? Because, like I said, you're not doing the same test. How does this test differ? First of all, the degrees of freedom is not even the same, right? So you can see that your degrees of freedom is different for the Welsh test because the formula is complex. It's a very ugly formula that almost no one likes to use. This is one reason why we really actually like to check for a pool t-test, because if we can avoid using the degrees of freedom formula for the Welsh's t-test, we will avoid it, right? The second thing is that, so that's one thing. And the p-value changes too, because of course the nature of the test is not the same. So the p-value you get is not the same because of the fact that the standard error is going to be different, since the degrees of freedom is not the same, the ratio of your actual normal to a chi, so it's always a ratio of normal to a chi, the ratio of this thing is going to change. And so this is something we have to keep in mind, right? So because the ratio changes since your degrees of freedom is different, we have to keep this in mind, right? So now you're doing a pool t-test and it's different, but the conclusion is still the same. Notice that you're still going to fail. You're still going to reject the null hypothesis, right? So the p-value is still very small. So you're going to reject the null hypothesis within the context of what you see in your data, right? Notice that notice that instead of having like a different from 2, as we had the one-sided task, the default is to assume your difference you're interested in looking for is 0. So you can see that it says that the true difference in means is not equal to 0. You can change that if you want to. If your difference is not 0, you can do as you did before with the one-sided task, so you have mu is equal to, and specify what your mu happens to be, right? So that will change the nature of the task. But the default is always to assume that you're looking for a difference of 0. If your difference is not 0, you can specify it inside this code, of course, right? And it will change again the nature of the task, right? That's one thing to keep in mind. So I'll just pick a note here. Of course, we can change the nature of the difference by, you know, adding mu equals, and then then means you're asking for different tasks. But again, you get a confidence interval, and because now the difference is you're looking for difference from 0. The question you're asking yourself about the duality between the confidence interval and the p-value is whether or not 0 is inside your interval. If your p-value is significant, as it is in this example here, 0 is not going to be inside your interval. So notice that 0 is not a root here because it's not inside here. This is a negative interval entirely, and 0 is to the right of it, right? So it doesn't cross. 0 is not in that interval. Whereas if this was a positive value, then of course 0 would be inside there, but it's not, right? So this means that it's significant. What it's saying is that if you sample infinitely often, a sample of size 32, 95% of the time, you will not find 0 in your interval, basically, right? I just want to point out one more thing, which is that the degrees of freedom for a pooled t-test, right? You have the following here. So this is for pooled, i.e. pooled, right? So if you have a pooled t-test, you will notice that you're doing n1 plus N2 minus 2 because you have independent samples and they each have degrees of freedom N minus 1, right? So then that's what you see here. So that's why you actually see in this console here, it now becomes degrees of freedom 30 because you're actually doing, 18 plus 14, which is 32, minus 2, which is 30. So now your degrees of freedom change as well, and things look more neat, basically. So it's not a trivial assumption, and so you should check. The other thing I'll point out, the last thing I'll point out is that these two questions, that notice that I didn't actually check whether or not these distributions were actually normal. So you should actually check to see if group 1 and group 2 have normal distributions, i.e. check the box plots or even the histograms, right? And convince yourself that it's actually normal. If it's right skewed, because Ken will always ask you this, and if it's right skewed, you should know if it's right skewed, right, before you actually manipulate the t-statistic. The other question you could ask yourself is, do you think that the sample size is large enough, right, within the scope of sample size, within the scope of group 1 and group 2 to perform the test? The t-test actually does okay with smaller samples, but it's still something we could actually ask ourselves. If we have like very right skewed data, and our sample sizes are very small, what does that mean in terms of the actual robustness of our t-distribution, right? So there's two follow-up questions you could always ask yourself, because at some point, especially this one, Ken will ask, did you check if your assumptions are violated? In which case you may want to look at your box plots, right? He may not even tell you to do that, but that's probably what implicitly he's asking you to scope for, right? Does anyone have any questions before we end for the day? Other than like, if I'm going to post it, of course I'm going to post the content. Does anyone have any questions about anything else before I? Oh, so I'm going to post this and then send the recording to Ken to post it on Quarkus. He'll post it on Quarkus for the class probably. Any other questions? Cool. So this is probably within the scope of your assignment.